Well, welcome back, guys. Hope everybody's doing okay. Um, I want to share with you the calendar through Canvas, so we make sure that everybody knows what's coming up and what's going on. Okay, today is the 6th. Obviously, we have a lab due today. Homework assignment for Saturday, chapters 10 through 11. Today, the plan is I will finish both chapters 11 and 12 because they're pretty short. We'll get those knocked out today. Next week, you have exam number 4, okay, which covers chapters 10 through 12. Now, if you haven't had a chance, in the modules, there's a number of worksheets that you can utilize to help you go through these questions that you may see, at the exam time. Also, we're looking down the road. We're getting close to the end of the semester. We have on the 4th of December, the final exam for the lab part, which you just encompass the, labs 6 through 11. Excuse me. Coming down with a bug, I think. Anyway, on next month, we have very short time. The 4th, like I said, would be the online final exam for the lab part. And then we will have the, that one's the final exam, which I'm going to move that. I can't move that. That's the 10th. Has to do with the requirements for me to get the, hold on, there's a problem here. Yes, there is. Disregard that 10th. There's a problem there. That's not the final exam. That's incorrect. I need to double check this because the final online exam for the lab only is on the 4th for sure, lab 6 through 11. And that one there that I'm pointing to, don't know what that is, but I'll check that and I'll correct that. Our final exam for the lecture part is scheduled for the 18th, and that's comprehensive chapters, all the chapters, okay? Excluding probably chapter 16. That's I don't think we're going to be doing chapter 16. It has to do with gases, and that's really an optional chapter. So I would be going just chapters 1 through 15. Okay. If you're not done the nomenclature exam, you have multiple attempts, get through it, try to get it knocked out because it does affect your grade quite a bit. You remember, as per departmental policy at SCC, you're required to have at least an 80% to pass that exam. So otherwise, I have to insert a 0 of anything less than 80%. And you may have seen already that I did insert, for those who haven't done it yet, a 0, so you can see where you stand, because it does have an effect on your grade, especially if you're on the border. It can drop you a whole letter grade, especially if it's 10% of the final exam. I did add a aid for you called StudyMate that helps you with respect to naming chemical compounds. You might want to zip through that and take a look. If you don't know where that is, let me show you. Down on your left, the far left column, you should see something called StudyMate. Okay, got a question here. My suggestion is to continue to take the exam. The question is, you wait to take the nomenclature. Right now, with the 0 in there, if you don't have it, that's your true grade and where you're at. Because the way Canvas works is If you have any assignments that have not been graded, that grade is not incorporated into your final grade. So if you miss, for example, homeworks, they may not have a 0 on them just yet because I keep them open toward the end of the semester. But if you put in a what if situation from your end, you put a 0 in whatever exam, or not exam, but whatever assignment you missed, that gives you a better feel for your grade. So yes, you can't go wrong by just taking that nomenclature. It's only 20 questions. Take it any number of times. There's no limit. And if you're happy with that 0 and you're happy with the grade, then that's your grade. You do what you want to do there. But my suggestion is just to keep plugging away till you get that 80%, and it just helps you overall grade wise. Okay. With respect to more assistance as far as helping you with nomenclature, I did send a PowerPoint slide and a Word document with respect to polyoxy or polyoxy acids and how to name them. I also have links there. I gave you a link to another video that pertains to polyoxy acids like nitric acid, nitrous acid, so on and so forth. Also, I've incorporated StudyMate, that if you click that, StudyMate, it sends you to this nomenclature practice. If you click on that, you can do any multiple things. You can create flashcards. There's 140 some different formulas and structures I put in there that you can, for example, nitrous dioxide, you flip the card, it gives you the formula. Okay, you can do that. There's 143 compounds there. Or you can fill in the blank where you're given the name, lithium hydroxide, then at the bottom, you put in the formula and it'll tell you, if it's correct or not. Okay, so that's another option for you there to help you out. So, all right, Nicholas, does that answer your question? As it stands right now, that if you're not past the 80%, there is a 0, and that is a clear indication of where you truly are with respect to your grade, with respect to the nomenclature part. Now, again, all the other assignments, with exception of the exams, are still open, though they do have a penalty. They are still open, so some grade is better than no grade, even though for the homeworks we do drop 2 of them. But you can always do your best to get that grade up a little bit greater, a little bit better. Also, there is a extra credit in the final grade section, final exam section or module, down at the bottom here, right here. It is a density extra credit. I believe it's 15 points. I'll check that. I believe it's 15 points. Basically, it's a file. You download the file, sends you to the link, a link where you have simulation for density. Just follow the instructions of the attached file. Once you're done, save your file, go back into the assignment and upload your file, and then I will grade it from there. Okay? So, and that extra credit would go into the final exam section. So all that would do for you will help improve your final exam percentage. Okay, any questions? Oh, yes. Also in the exam section, there is a lecture, instructor lecture and evaluation. It's not open till I believe the 11th. And what that is, there's 2 links in there. One for the lab section, one for the lecture section. Series of questions or evaluations on the course and on me. I don't see anything until next semester. Please feel free to give us any type of suggestions with respect to this coursework. We've had to change very quickly from face-to-face to online. So we were putting things together very quickly. And so obviously, I suspect that we're going to continue with online for a while, and even in the future, it's going to be part of the coursework that you're going to find in schools, where you're going to be offered more online classes than you are now. And so whatever suggestions you see from your perspective, please feel free to put that in there, because we definitely would consider it. Okay. All right. And also, 5 points extra credit. Basically, you go in there, answer the questions, and then when you're done, go back into the evaluation, and then submit I done it. And then when I get my alert that you done it, I give you your 5 points that will be a part of the exam section, total percentage. There are a couple of you that I did do another extra credit. There's a couple of you that didn't do it. It was just to check to make sure your lockdown browser was working. But there's another opportunity there, if you've not done it, to pick up a few extra credit points. Okay. Any questions? Yeah. All right. Feel free to do these activities ahead. You know, this class has been classified as on your time, so you're not. Even though I do put deadlines for homework, you know, you're more than welcome to jump ahead and get them done earlier than the due dates. Okay. Now, next semester, this class is the lab is going to be on your time, but the lecture is going to be live. So it'd be similar to a class, except you can do it online. So you'll be required, they will be required to attend lecture, or in this case, Zoom lecture. All right. Any other questions or comments? No. All right. Well, let us jump into, let's make sure I got the right number 11 here. Okay. Very short chapter. We call that thermodynamics. Okay. And with respect to thermodynamics in itself, what we're giving you here is just like the tip of the iceberg. Thermodynamics is a whole group of science, both in physics and chemistry, that it's a big topic. So, but we're going to give you just a little bit about it. And if you look at the name itself, thermal meaning coming from the term from heat or energy, dynamics meaning things, the movement of things and how things move around. Okay. Now, when it comes to chemical reactions, we have what's called a collision theory. And that if we look at this very general, I call it a cartoon diagram, we have two diatomic molecules of some species coming together on the far left and coming together to break that bond. In other words, what's happening here is, let me find my tool here. Marking tool. Okay. What we have here, obviously we have a bond sitting right there between the two atoms in that diatomic molecule. And we also have a bond sitting there. Well, notice that they have to come together with a certain specific orientation, okay? And they pass through this process that we call, we're going to give it a name, it's called the transition state. This is an area where, if we look at this, the bond that was there initially is being broken, but at the same time, we are creating a new bond for a new type of molecule or compound, okay? So the transition state is that point where we got simultaneous bond breakage and bond formation, new bond formation. Finally, we make the products. This is where the products are at, sitting right here, okay? We created something now with a yellow and a bluish green sphere, some new compound, okay? And having to go through that transition state, okay? Now, the orientation is very specific. They have to orientate just right to create the new bond. Not only do they have to orientate just right, they can have a specific amount of energy to overcome so these molecules can make the product, okay? It's a very specific type of energy. We call that the energy of activation. And so these molecules don't have the correct orientation, they don't have the correct amount of energy necessary, then products are not formed. Now we take it for granted that there's molecules that are happening in our body and there's reactions that are occurring, but it's mind-boggling when we think about it that, there's a good chance that some of these reactions, specifically the biochemical reactions, don't occur because of all these factors have to come into play just right for products to be formed. And even in the reaction, if you're in the lab, and you put A and B together and you're hoping to get C, and you run the reaction and nothing happens. So you do a number of things. You kind of heat them up a little bit, but you got to be careful with the heat. You can't give it too much heat because there's a chance of degrading the reactants. All right, or you give them too much heat, and instead of a product that you're trying to make, you make something else. So there's a lot of variables going on. And orientation, for example, is very specific. It's like shooting pool. You're shooting pool, you're trying to make that ball in the corner pocket. You got to angle it. You got to hit it just right with just the right amount of energy. You got to hit that cue ball with just the right amount of force and the right amount of angle to get that ball in the corner. Well, chemical reactions are the same way. If you hit that cue ball too hard, you're not going to make that corner pocket. Might kick it out of the table completely. Or if you don't hit the right angle, you don't have the right angle to make that corner pocket. Chemical reactions are very, very similar. Okay, so to have a successful collision, all right, we can do a couple of things, all right? We need to increase the number of collisions. That increases the probability of two reactants coming together. So we need more collisions to get things to work. Or we can give it more energy. That energy I just talked about is called the energy of activation, and we denote it by the letter E with subscript lowercase a. That is the minimum amount of energy necessary for two reactants to overcome to become product. Okay? And we'll have a diagram to show you where this energy is at and what it is. Molecules have to be orientated correctly. Without the correct orientation, they just bounce off and then no product is formed. Okay. We can increase the rate of the reaction. And again, temperature does that. You notice that sometimes you might think, well, I got to cook something in the kitchen. I want it to cook a little bit quicker. What do? I heat it up a little bit, turn the heat up a little bit. That does make things go a little faster, but you got to be careful. Don't heat it too much and you might destroy everything. Okay, we can increase the rate by adding more reactants. That's one way to do it. If I got 10 molecules of A, 10 molecules of B, I'm hoping that they get together to create whatever C they're going to make. But one way to increase the chances, instead of having 10 and 10, now what if I get 1 billion of A and 1 billion of B? Now I've increased my chances of those two coming together to make a product. So I can increase the temperature, I can increase my concentration of my reactants, okay? Obviously, the temperature increase, it causes the molecules to move a little faster, okay? But again, we got to give it just the right amount of energy, because if we give it too much energy, it's like that shot in the cue ball. If I hit that cue ball too hard, I'm not going to make that corner pocket, because I'm going to cause that ball the ball to maybe fall off the table or not give it the right angle and miss that corner pocket completely. Okay. or we can add what is called a catalyst. Okay, now what a catalyst does is basically this. Like I stated, all reactions have this energy of activation, the amount of energy necessary to overcome so they can become products. What the catalyst does, it comes in here and essentially lowers the energy of activation, therefore allowing those two reactants to become products. I can do that in a number of ways. Most of the time what it does is it basically orientates the A and B to have the same orientation, or the correct orientation, I should say, so reactants can proceed. Or it may even transfer energy to them so reactions can proceed. But basically, it's get them together so a product can be formed. Now, once they're done, that's it. The catalyst goes on and does the same thing with another set. It's not involved in itself directly with the reaction, but what it does, it lowers the energy of activation. Our body is loaded with catalysts. We call those enzymes. Without them, chemical reactions, life as we know it wouldn't exist, because if we were to let these reactions proceed at their own rate, nothing would happen. And thank goodness for catalysts in our body for it to react. And we use catalysts for a number of things. Metals, for example, metal ions are catalysts. I once had a reaction that essentially literally blew up in my face. I just stepped away and the whole thing went boom. What had happened after we analyzed what went wrong was in cleaning up the glassware, there was residue iron 2. And that in itself functioned as a catalyst for that reaction I was working on. And it made the reaction go very quick, so quick that it went boom, it exploded. And so catalysts can be very effective. Okay, as I mentioned, energy of activation is the minimum amount of energy needed for a reaction to occur, to turn reactants into products, okay? We also have equilibrium reactions. This concept was introduced when we talked about weak acids. In weak acids, we talked about how the acid itself doesn't dissociate 100%, and weak bases, but they dissociate much less. And so C and D here could represent the ions as dissociated, but A and B can represent the material that is still intact. And so we had the rate of the reaction, in other words, it was a double arrow. The rate going forward and the rate going backward is pretty much equal. Now, we also talked about this somewhat when we talked about buffers and when we talked about acids. I mentioned that buffers, one buffer in your body was a pH buffer. It tries to maintain a pH buffer around 7.3, 7.4. And that's an equilibrium reaction. So if you got too much acid in your body, in your blood, then it reacts with the base of the buffer to maintain that pH. So the rate going forward and the rate going backwards is the same, okay? Now, what do we use here? We call them, how do we describe everything we just talked about? Well, we have what are called energy profiles, and I'll get more detail here in a second, but I kind of put the graph on the top right corner. We have the transition state that I mentioned, okay? And it's denoted there on the very top of the peak of that hill there. That distance from where the reactants began, that energy level, to the transition state, that energy level, that energy, which is denoted there by EA, that is the energy of activation. That is how much energy is necessary to overcome so you can go to the far right of that graph to become products, okay? So transition state is the top of the hill. Now, delta H, we call it the change of heat energy, basically, or the reaction. That is the energy content of the products minus the energy content of the reactants, okay? And so that graph up there, you can see that the energy level of the products is much less than the energy level of the reactants and where they began. That is a graph. On the x-axis, we call that the rate of how the reaction is proceeding. It's like taking a snapshot of the reaction as we go across the x-axis. The y-axis, that's the vertical one, that's energy. And we can put energy markings there and put arbitrary energy units. But you can see that the product's energy level is much lower than the energy level of the reactants when they began. Keeping that in mind, because if we calculate delta H, the energy level, we end up with a negative number for that particular graph, because the energy level that could be, let's say, arbitrarily 10 units of energy, okay? And the reactants begun at maybe 30 units. And so we got 10 minus 30, guess what? We end up with a negative 20 units of energy. That's what the delta H is calculated as. That negative value tells us something very important. It tells us that it's an exothermic reaction. In other words, it gave up heat during the reaction. I'll have that graph here in larger scale, and we'll go through that more detail here in a second. Okay, and so we have two types of reactions. We have an endothermic and an exothermic. Now, endothermic reaction, energy is required for the reactants to become products. And so energy is, or heat energy, they're analogous, okay? They are a reactant. And so it requires energy, and generally what happens, it takes it from the environment. So an endothermic reaction absorbs heat, resulting in a cold reaction. Classic example of this, if you go to the pharmacy, for example, and you buy a cold pack. You buy this cold pack and you smack them. There's two chemicals in that plastic container. You got to break them up, you got to break it, smack it to break the material in that's holding the reactants so they can interact with each other. And it gets cold as the reaction proceeds. So you can use that cold pack for your, sore muscles or whatever. That's an endothermic reaction. So energy was taken from the environment, okay, hence resulting in cold. The opposite of that is an exothermic reaction. And in that scenario, let me clear that. The heat is a product, okay? And heat / energy is a product. And so this reaction gets hot when the process proceeds. Again, back to the pharmacy, go to your local CVS or wherever, you can buy a hot pack. Same scenario, you take the hot pack, smack it, chemicals mix up in there, it gets warm. It gets pretty warm, okay? That's an exothermic reaction, exothermic. Now, with respect to the energy profile that we have up on top, when you have an exothermic reaction, that graph in the top right corner demonstrates an exothermic reaction because the energy of the products is much less than the energy of the reactants. And so in that example, we got 10 energy units for the products, say 30 energy units for the reactants. 10 minus 30 gives us negative 20 energy units for delta H, okay, which tells us an exothermic process with a negative value for delta H. And this is the way when we do it. So we got the energy on the x-axis, and we can graph these. So we can put a scale here, and we can arbitrarily put energy units. Bear with me for a second. Okay, and so we could arbitrarily say, all right, well, here this point here, we start off at 10 energy units, and we go 10, 20, 30, maybe this is 40 over here, okay? And going in the other direction, they're not energy units, but it's basically a snapshot of the reaction as it proceeds. If we were to take a little snapshot and take a picture of the reactants, we could see A and B together. There's the reactants, and then as they proceed, you can get up to the transition state, and finally they become products over here on the far right. All right, so in this scenario, after the reaction proceeds, okay, we have, for example, the products end up with the X amount of energy. So we can extrapolate to the graph. And so products are at 10 energy units. Remember that scale, we've arbitrarily just made some numbers. Energy units. Energy has specific values. For this case, we just call them energy units. And the reactants, guess what? They started off, let me change the color a little bit. They started off in the X amount of energy units, say 40 energy units. The reactants ended up with 10 energy units. And guess what? The transition state, when it hit the top of the hill, it ended up with an X amount of energy. And we could say, I don't know, let's arbitrarily say, proceed with the scale. We can say, okay, that's 100 units of energy. Okay. And so we can see here that the energy of activation, okay, is the energy level of the transition state, which is 100 units, and minus the energy units of the reactants where they started. So that difference there is 60 units of energy. So the energy of activation for this particular reaction is simply what we got, 60 units of energy. Okay. That's how much energy is necessary for these reactants to overcome to get to the transition state. Okay. Now, if we look at delta H, and as the energy of the reaction, we were at 10 units is the products, and reactants started at 40, and so delta H is equal to the product energy level minus the reactants, which is equal to negative 30 energy units. Okay. So in this scenario, we can see that the question being asked is delta H positive or negative? Or we can see based on the position of where the products finally ended, which is about 10 energy units, and arbitrarily just gave it 10 units. And the reactants were I have a negative value. Being a negative value tells me that it is exothermic, okay? So when delta H is negative, it is exothermic, and it gives off heat. So you can see without having to go through the calculations that when the product level, when the energy levels of the products, okay, when the energy level of the products are lower than the energy level that the reactants began, we have an exothermic reaction and a negative delta H. In this scenario, it's the opposite. Notice what's happened now. Okay. The final energy level of the products is much higher than the energy level of the reactants. So when I calculate delta H, I end up with a positive number. Okay. So in this scenario, that graph would display an endothermic process just by analyzing where the products and the reactants are with respect to their energy level. So be able to, one, look at the graph and be able to label the transition state, where delta H is, where the reactants begin, and where the products end up as, okay? And be able to label energy of activation, okay? Also think about what kind of things you can do to get the reaction to work better, increase the rate, increase the temperature, increase the concentration, what factors affect the reactants to become products, orientation, the manner in which they come to and attack with each other to form a product. That's crucial. Okay, those are the key points we want you to take away from this particular chapter. Let me clear this up. So, typical question. Oh, did not clear up. Typical question here is you're given a graph. They're asking you, okay, is this endothermic or or not? Well, obviously you can see that the product energy level, the final energy level of the products is much higher than where the reactants were. Therefore, this would be a positive delta H value. Therefore, an endothermic reaction. Therefore, it would be a cold reaction. It would get cold because it's taking energy from the environment, and energy is required as a reactant. The exothermic energy is a product, okay? It gives off heat. So here's the shot of both of them. A exothermic process on the top graph and an endothermic process in the bottom graph, okay? All right. Now, what does the catalyst do? Well, simply put, what a catalyst does is lower that energy of activation energy, denoted here by the graph. You can see where that graph is for normal reaction without the catalyst. And then what happens is by using a catalyst, the energy of activation now is much lower. So it could be, let's say, energy of activation without the catalyst could be 100 units, with the catalyst maybe 10 units. And so it doesn't take much energy for it to become products, okay? Catalysts are very, very important for multiple processes, not only biological, but all around us. Okay. That being said, folks, that's all I got to say about chapter 11. Okay, it's very short. Like I said, look at the graph, be able to label the different positions here for reactants, products, transition state, energy of activation, delta H. Being able to look at the graph, determine whether it's endothermic or exothermic, what factors are involved as far as reaction, energy is a factor, concentration is a factor, orientation is a factor with respect to reactants coming together with the right orientation so you can make product. Okay? All right. Any questions?
I think I'm good. Thank you.
All right. Sounds good. All right. Now, let's talk about mole. No, let's talk about the mole. Now, this concept sometimes can be very challenging also to students. But if I mention to you a dozen, what number do you guys think of? What do you think about when I say, okay, I got a dozen donuts? How many donuts do you have?
12 donuts.
Exactly, 12, right? And if I say to you, okay, half a dozen, how many donuts do you have?
6 donuts.
6. And what about if I said a quarter donuts? A quarter dozen, I should say.
3 donuts.
3 donuts, right? Because we grab that concept of a dozen, okay, because it's a small number. 12. The mole is nothing more than a number. It just happens to be a very big number, okay? Now, we call this Avogadro's number. Now, this is going to have you go back and review how you type in scientific notation in your calculator, because this number is 6.02 times 10 to the 23rd units. It could be anything. It could be atoms, it could be molecules, it could be ions, it could be bananas, oranges, apples, whatever. It's just a number, okay? I said a dozen donuts. Okay, we're talking donuts, but I could have said a dozen eggs. Same scenario. It's a number, okay? Here's a picture of Avogadro. He's the scientist that came up with this number. Now, how big is this number? Let's put this in perspective. All right. This number is 602 sextrillion. I see that I put a scale on the far left to give you an idea where you're at. A billion has 9 zeros, okay? A sextrillion has 21 zeros in that number. And it's, you know, we go all the way down to the bottom where you have Googleplex, which is a Google of zeros, a whole bunch of them. You know, big numbers. Now, if you were to count Avogadro's number and you were able to count one number per second, that is your rate. 1, 2, 3, 4, etc., and you're counting at one number per second, it would take you roughly 19 quadrillion years to get to the last number of Avogadro's number. That's how big it is. Yeah, humongous number. And this number really mind boggles me, because you're gonna see why here in a bit. It's a number is tough to visualize. Now, if we had a mole of softballs, okay, and a softball, I don't know, roughly about 4 or 5 inches in diameter, okay, not a baseball, but a softball. If we had one mole of softballs, then all that would be approximately the size of the Earth. You know, that's a lot of softballs, okay? But they're tiny because our atoms are very, very tiny. But we got a lot of them. Okay, on the periodic table, I keep referring to it, and I'm referring to it again. When we were talking about the atoms or the elements, you know, we talked about the symbol, we talked about the atomic number, but then we talked about the atomic weight, okay? For titanium, for example, it has an atomic weight of 47.88 units. Those units are called grams per mole, okay? Grams per mole. Now, you might think, well, wait a minute. Let's think about this for a second. I'm going to use eggs as an example. Okay. Let's say we got small eggs. Okay. And for argument's sake, we're going to say that they're going to weigh 100 grams per dozen. Okay. Which is equal to 100 grams per 12, correct? Does everybody agree on that? Okay. All right, so let's go to medium eggs. And for argument's sake, we'll just say 200 grams per dozen. And we'll go large. And we'll keep it at 300 grams per dozen. Okay. Now notice, obviously in every case here, small, medium, and large, I have 12 because I got a dozen, right? Also, they're going to weigh differently. If I have 12 small eggs, they weigh 100 grams. If I have 12 large, medium eggs, they're going to weigh 200 grams total. And by the same token, 12 large eggs will weigh 300 grams based on the arbitrary numbers I put up there. Okay, but I can also ask you a question. If you had, for medium eggs, If you had 100 grams of medium eggs, can you tell me how many dozen you have? How many dozen would 100 medium grams be? Oh, got some answers here. Half a dozen, right? Because we know for medium eggs, all right, a dozen weighs 200 grams. Therefore, if I have 100 grams, I have half a dozen eggs, which means how many eggs do I have? 6, right? Because I got half a dozen. All right. And I can do the same thing with the large eggs. If I said I had 150 grams of large eggs, I would have a half a dozen eggs, which meant I got 6, so on and so forth. Okay. Well, the same concept I want you to bring forward to the atomic weight of the atoms. Because, for example, carbon, the atomic weight of carbon is 12.01 grams per mole, which is equal to 12.01 grams per 6.02 times 10 to the 23rd atoms of carbon. Okay. And so weighing out 12.01 grams of carbon gives me exactly 1 mole. Just like the medium eggs, I weigh out 200 grams of medium eggs, I got a dozen. Okay. And if I weigh out 200 grams of medium eggs, I got 12 eggs. Well, in this case, with respect to a mole, if I weigh out 12.01 grams of carbon, I have 6.02 times 10 to the 23rd atoms of carbon. If let's take another one, let's say nitrogen, its neighbor. And that should be capital C up there, not little c. Okay. The atomic weight for carbon is 14.01. Let's take, yeah. Now, speaking of atomic weights, when you're asked to do any calculations with atomic weights, do use the atomic weights on the periodic table we have. Okay, because if you go do a search for atomic weights, you're going to see a variety of different numbers. And Canvas is set up to look at the answers based on the atomic weights of the periodic table that we have. Okay, so do use the atomic weights of the periodic table that we utilize for this class. Also, you may find homework that says refer to the pink periodic table. Okay, that's the same periodic table. The reason it says pink is that periodic table normally is printed in pink paper, and those are passed out to students when we're in class, because they utilize that during exams. Okay, so anything that says pink periodic table, same periodic table we're using. All right, so nitrogen has an atomic weight of 14.01 grams per mole. Okay, which means if I weigh out 14.01 grams of nitrogen, I have 1 mole, or 6.02 times 10 to the 23rd atoms of nitrogen. Okay, just like the large eggs. If I weigh out 300 grams, I have a dozen eggs, large eggs, which means I got 12 large eggs. Obviously, the large eggs weigh more because they're bigger in size, right? Well, nitrogen weighs more because it has what? 1 more proton and some more neutrons, right? It's a bigger atom. So it's going to weigh more. But the concept of the mole is still there. I have 1 mole. Okay. Now, when it comes to sig figs, and I know you're probably thinking, wait a minute, I thought we were done with sig figs. No, sig figs are always used in science, significant figures. When it comes to sig figs, we don't use the atomic weights to determine how many sig figs you have. simply because, if you recall, when we were talking about the atoms, there are isotopes of these elements. Carbon had carbon 11, carbon 12, carbon 13, carbon 14. Remember those guys? Okay. Well, each one had a different abundance in nature. Carbon 12 is the most abundant, like 98%. All right. And so the point being is that number 12.01 is the average of those whole numbers, carbon 11, 12, 13, and 14. And so technically, when we average whole numbers, you have an infinite number of sig figs. So we don't utilize atomic weights for determining significant figures simply because they have an infinite number of significant figures. All right. So just remember, I don't use atomic weights. Atomic weights for determining sig figs. Anyway, so the concept of a dozen, the concept of the mole is nothing more than the chemist dozen, the physicist dozen, okay? It just happens to be a very large number. So let's go back to the chapter. And so we can look at all the atoms on the periodic table, and we know its atomic weight, okay? And for every atomic weight on the elemental in the periodic table, that represents 1 mole. The atomic weight has units of grams per mole. Okay. Now, as I mentioned, the mole is nothing more than a number. It could be anything you want to count. We in chemistry, obviously, we're going to talk about atoms and ions and molecules or units like sodium chloride or aluminum oxide, but you could be talking about bananas and oranges or whatever you want. It's just a number. It happens to be a big number. Okay. And so if we look up the concept, I used the term molar atomic weight when I talked about the atomic weight of the elements. Generally, that's what they're called, atomic weights. But we also introduced what's called the molar mass. And they're used interchangeably. The molar mass, atomic weights, they're used interchangeably. They have the same units, grams per mole. When we start calculating the molar mass of molecules, what we start doing is adding up the atomic weights of all the atoms that are in the molecule. And so we tend to use the term the molar mass for molecules. And when we talk about the element itself, we're talking about the atomic weight, but they're interchangeable, like I said. So when we talk about the molar mass of carbon, all we do is find its atomic weight in the periodic table, okay? And again, this could represent small, medium, and large eggs, right? Obviously, gold are the large eggs, sodium would be the medium eggs, and carbon could represent the small eggs. They all have a different weight, but they all have 1 mole or 6.02 times 10 to the 23rd atoms. All right. It's an interesting concept if you think about it. Because if I weigh out, you go to the lab and I weigh out 12.01 grams, I have 6.02 times 10 to the 23rd atoms of carbon. And if I weigh out 24.02 grams, guess what? I got two moles or twice that number. Okay, no different with the small eggs. If they weigh 100 grams per dozen, if I have 500 grams of small eggs, guess what? I got 5 dozen. Okay. All right. So the molar mass. This is where we have to add up. We're going to need the molar mass here for a lot of things for calculations. Is the mole? The concept of a mole is very important. Because when we look at reactants, let's say reacting A plus B, if we're doing a reaction, we're going to take 10 grams of A, for example. Well, we can't calculate how many grams of B we need directly. We have to convert the grams of A into moles to figure out how many moles of B we have, to figure out how many grams of B we have. So moles is our common factor when we're going from apples to oranges, so to speak, okay? So the concept of moles is very important. And it's also related to the balancing of the equations that we did earlier. When we balance equations and we put the coefficients up front, we talked about 1 molecule is required of A for every 2 of B. And now we can convert that term molecule to moles. 1 mole of A may need 2 moles of B. And guess what? We have a ratio, 1 to 2, in the balance chemical equation. We have a ratio here too. Avogadro's number is a ratio, 6.02 times 10 to the 23rd entities per mole. That's our ratio that we can write it just like I stated or inverted. Okay. This brings us back to when we were doing conversion of units. So we talked about writing every conversion factor was a ratio that we can write however way we needed to get rid of the units that we want to get rid of. The units that we want always were in the numerator. We'll have more to say about that. But that aspect is coming back here. Okay. So to calculate the mass of barium hydroxide, the first thing you got to do is we need to write the formula for barium hydroxide. Okay. So this is where the previous chapters come into play. Okay. Well, you're given the name barium hydroxide. My suggestion is to first, before you write anything, is to put everything into ions. And we know that barium has a +2 charge. How do we know that? Well, barium is in group 2A, okay? Has 2 valence electrons. That's point number 1. Number 2, barium is a metal. Okay, now you forgot where the metals are. Look at the periodic table. The periodic table has a stair step. Everybody to the left of the stair step is a metal, with the exception of hydrogen. That's the far left in group 1. That's not a metal. Okay, so barium is to the far left of the stair step of the periodic table. Second of all, it is group 2A, which has 2 valence electrons. And third factor is this: barium being a metal loses electrons when it becomes an ion, and it's going to lose those 2 valence electrons. Therefore, it will have a +2 charge. Because barium had 56 electrons. I was taking 55, but it's 56 electrons. Okay. When it becomes an ion, it lost 2 of those. So now it has 54 electrons, but it still has 56 protons. So the 56 positives, 54 negatives, net +2. All right. The hydroxide, very important polyatomic ion. Why? We had a whole chapter on acids and bases. Okay, so we have a base here. And so the hydroxide ion, polyhydroxide ion, was OH negative. If you forget what it is, but recognize the name, but forget the formula, go to the periodic table. The table that has the polyatomic ions, you'll find it there. The hydroxide has a formula of OH minus, okay? So now I've written barium hydroxide in ionic form. Write those in ionic form first so I can know how many of each I need to put together. Why? When I put my positive and negatives together, I got to put enough of each so they cancel each other out. So I can see that I only have 1 negative, but I need 2 of them, 2 hydroxides, to cancel the +2 of barium ion. Okay? That being the case, that 2 in front of hydroxide becomes the subscript for the hydroxide, because I need more than 1 hydroxide. Therefore, I got to write a parentheses, put that 2 in subscript of the outside that parentheses. It tells me I have 2 hydroxides. So that is the formula for barium hydroxide. Okay. Now what I do, I use the periodic table and I look up the atomic weight for all the atoms in the formula of barium hydroxide. So I got 1 barium, I got 2 oxygens and 2 hydrogens. Okay. Doing that, barium is 137.33 grams per mole. There are two oxygens, each with a 16 atomic weight of 16. Okay. And there are two hydrogens, each with a 1.01 grams per mole atomic weight. Tally all that up. The molar mass for barium hydroxide is 171.35 grams per mole. Okay, grams per mole. Let's take a minute and figure out the molar mass of water. H2O. What do you think the molar mass of water would be? Well, anybody know offhand real quick? Well, oxygen, what's the atomic weight of oxygen? 16, right? It's given to you right there. You only have one. And what is the atomic weight for each hydrogen? 1.0, yeah, 1.01, that's correct. And we've got two of them. So the molar mass for water would be what? 18.02 grams per mole. That look about right? Check my math.
I think that looks good.
Yeah, 18.02 grams. Now think about this for a second. If you weigh out 18.02 grams of water, okay, and let's say pure water, you have 1 mole of water molecules, or 6.02 times 10 to the 23rd molecules of water in that 18.02 grams. Okay, that's a lot of molecules, right? Now think about all the water in the world, just the world here on the earth, and try to calculate. I couldn't even guess how much water is out there, but if you knew that number and then calculate how many molecules of water, that number would be astronomical. My God, even if you just got a glass of water and figure out how many grams a glass, well, you know, let's say you took 100 milliliters of water. That's roughly 100 grams, you know, 100 grams of water, or call it double that, say double 180 grams of water. My God, you got 10 moles of water molecules, or 10 times 6.02 times 10 to the 23rd. That is a lot of water molecules, you know, a lot. And so that gives you an idea how small these atoms are. And now think about all the water just in your body, and think of all the water molecules that are there. It just mind boggles me with that number. Anyway, so that's how we calculate the molar mass, and that's of anything, any compound that's thrown at you. You simply add up how many atoms each one brings in, okay, to the formula. Obviously, if you don't know the formula for simple ionic compounds, we've gone through writing formulas out. I went through the exercise of how to figure out the barium hydroxide. So that's why we have to know. Remember now, we started off with the elements, and then we talked about the elements. We talked about the electrons in the elements and their electron configuration, and that led us into why metals lose electrons and why nonmetals gain electrons to form ions. And then we start putting ions together to write formulas, okay? And we start learning the names of these compounds, so we can take a name like barium hydroxide and write a formula. And now then we're going to start talking about reactions now, how we got these compounds to react with each other to do different things, and calculate how much of A reacts with B to give us how much product. Okay, so it's all tied in together. All right, so going back to Avogadro's number, as I mentioned, it is a ratio. Okay, And like any ratio that I've talked about, you can write it in one or two ways. And how you write it depends on how you need to use it. And thing to remember about a ratio with respect to units is the units you want to keep always are in the numerator. Why? Because the units in the denominator, you're going to do something to it to get rid of it. Okay? So Avogadro's number is written one or two ways up here as shown in this particular slide. And the question here is asked, well, how many calcium atoms are in 2.5 moles of calcium? Now think about it for a second. Okay, 0.25, that's a quarter, isn't it? That's a quarter of a mole. And so your number should be much less than Avogadro's number, because we're saying you got a quarter of a mole of calcium. How many molecules is that? So keep that in mind when you do your mathematics, because when you sometimes we're very quick just to plug the numbers in a calculator and just report that answer and not really think about the answer, okay? Anyway, so here we have how many calcium atoms are in a quarter mole of calcium. That means identify what you are looking for unit-wise. They're asking you how many calcium atoms are needed. So that is the unknown. So we're going to need Avogadro's number written in that particular form because we're given moles and we want moles to cancel. So we're going to be using Avogadro's number written on the far left. And you can see here that moles cancel, okay, leaving me with atoms. And then doing the math, so here we go again with scientific notation. Remember, refresh your memory how to plug that number into your calculator. And that number we get is 1.51 times 10 to the 23rd, which is less than Avogadro's number. And that is what we expect because we're only starting with a quarter mole. And that's what I mean by analyzing the mathematics to make sure that that answer makes sense. If you had a number that was greater than 6.02 and knowing that you're multiplying by a fraction, then something went wrong in the calculation. If this number was 12 point something, then something went amok, okay? So look at that answer. Make sure it makes sense. All right, second question. Calculate the number of moles of 3.75 times 10 to the 27th molecules of oxygen gas, okay? And so let's clear this up a little bit so we know what we're looking for, okay? They're asking you to calculate the number of moles, so that's what we're looking for. And they're giving you how many molecules of oxygen. So that suggests that I want to use Avogadro's number as written on the far right with moles on the numerator. And with that being the case, I run through the math and check my units. This MLCLS is shorthand for molecules. So molecules cancel as expected because I set up properly. Okay, and I end up with a number of 6,230 moles of oxygen, okay, which is consistent with the numbers that you are dividing. All right, first of all, you're dividing with a very large number, 3.75 times 10 to the 27th. You're dividing that big number by smaller numbers, so I should get a very big number. In this case, over 6,000. Which is consistent. If that number was different, if this was a fraction in your answer, that meant that you inverted the 10 to the 27th and 10 to the 23rd. That means you divided by a very large number. So you ended up with a fraction. Okay. So do look at your answers. Make sure they are consistent with the mathematics that you did. All right, so in these examples, and we're pretty much finished here with this chapter. It doesn't take much for to knock it out. Here you're being asked a couple questions. Number one, they're asking you How many grams is 1.667 moles of oxygen gas? All right. Now, the thing to remember here, let me make sure. Well, they're asking you here this question. Oxygen gas. Now, is that different from if it said moles of oxygen? Is that a different, instead of, for a minute, let's assume gas, the term gas was not there. Okay. Is there a difference with or without the gas in the sentence?
Would it be no, because the molar mass on the periodic table is in the usual state, which is a gas?
Yeah. Well, 50% correct. Okay. All right, because the term says oxygen gas, and what do we know about oxygen in its natural state?
That in its natural state, it's typically a gas.
Yeah, but have no fear of ice cold beverage. Remember that? It's diatomic. There you go, Rebecca. Okay, so the same would be true if they would have said hydrogen gas, okay, oxygen gas, and nitrogen gas. If they would have said just oxygen without the gas, then they're talking about the atoms. But here you got to remember they're talking about the gas. And when they say the gas, we're talking about its natural state. And yes, each oxygen is 16, but because it is the gas, it's diatomic, so its molar mass would be twice that, right? 32. Okay. So when you read the questions, be careful, make sure that they're not saying gas, because if they say gas, then they're talking about the diatomic element. Okay. And so we need to, we're going from grams to moles. Here's the thing to remember. Molar mass has the units of grams per mole. Now we can write it as moles per gram. Okay. And so if the question asks you how many grams is how many in this number of moles, that should give you a flag to tell you, I need molar mass. Why? Because the units are grams per mole. Okay. The same thing here. Second question, how many moles are in grams? 45 grams of silver. That tells me I need the molar mass of silver, because the molar mass of silver is grams per mole. And the same scenario here, they're asking you for grams again, but this time they're asking you about moles of water. And now to get the moles of water, I need the molar mass of water, which is the exercise we did earlier. So that's where you add up all of the atoms and all the in this case, 1 oxygen and 2 hydrogens to give us 18.02 grams per mole. And then finally, the last one, they're asking you, wait a minute, hold on. You're going to grams, but you're starting off with atoms. Now, I can't go directly from atoms of anything to grams unless I have a conversion factor there, and that is Avogadro's number, right? Because Avogadro's number gets me from atoms to moles. Once I'm in moles using the atomic weight or the molar mass, I get to grams or moles of potassium. Okay, we'll go through that here. Let me show you how I set these up. Let me clear this up. Oh, that's crazy. Okay. Now, the first one, they ask you for how many grams is 1.667 moles of oxygen. You have to recognize that we're talking about oxygen gas. And I need the molar mass to go from moles to grams. But I need the molar mass of oxygen gas, which is diatomic, which is 32 grams per mole. Okay? If that question would have just said oxygen, then it would have been 16. But they're talking about oxygen gas. All right, let me change the color a little bit there. All right, so look at my units there. My moles cancel. So now it's a matter of taking my moles, 1.667, and multiply by the molar mass. And here's something you see, you start picking up a trend. When you have moles and I want to get to grams, guess what? I multiply by the molar mass. When I have grams and I need to get to moles, guess what? I divide by the molar mass, okay? And I dividing them, flipping my ratio of my molar mass. I mean, remember that molar mass could be written as grams per mole or moles per gram. Which one I need depends on what I'm looking for. The question with the silver, they tell you, they give you 45 grams of silver and they want you to determine how many moles of silver, okay? So that is given, 45 grams of silver. I'm looking for moles of silver, which means that I need to write the molar mass of silver with moles in the numerator. Why? Because my grams will cancel out when I do the mathematics. So 45 grams is equal to 0.42 moles of silver. All right. And finally, second to the last one, they want you to calculate the grams of water are in 0.554 moles of water. Okay. All right. So I have moles. I want to get the grams. I need to take the molar mass of water with grams in the numerator. Okay. And so you can see the trend here again. I have moles. I need to get the grams. I multiply by the molar mass. I have grams. For the second one, I need to get to moles. I divide by the molar mass. Let me clear this up a little bit. I have moles. I want grams. I multiply by the molar mass. I have grams. Given grams, I need to get to moles. I divide by the molar mass. Okay. Then finally, the last one, you're given atoms. Okay. Well, I can't go directly from atoms to grams without going through my Avogadro's number, because Avogadro number equates the number of whatever I have per mole. And this factor is 1 mole is equal to 6.02 times 10 to the 23rd. So I write it with Avogadro's number in the denominator because they're going to cancel out. Okay. That puts me with the first factor, puts me in the moles of potassium. Once I know the moles, I multiply by the molar mass. So in this case, I have two factors here to get me to grams. Okay. So you can see how that large amount of atoms of potassium, 4.75 times 10 to the 16 atoms, that's a big, big number. But it only weighs 3.09 times 10 to the negative 9 grams. In fact, most balances in the regular lab wouldn't be able to even pick that weight up. Most balances weigh 2.0001 grams. Be tough to weigh that small amount. Okay. All right, which brings us to the topic of what we call molar volume. Okay. Now, this is only true for a certain set of conditions. And those certain set of conditions are called STP, standard temperature and pressure, which is 0 degrees Celsius, 0, oh, 0 Celsius, and 1 atmosphere, okay? So basically freezing point of water, and in 1 atmosphere. 1 atmosphere, that's a degree of pressure. Right now, it's here in Phoenix right now, Phoenix area, we're roughly at 1 atmosphere of pressure, okay? If we were to do 2 atmosphere of pressure, you begin to feel it. In fact, as you go deeper, I believe like every 10 meters down in the water, you increase by one atmosphere. So if you went down to 20 meters down into the water, you feel the pressure. Okay, that's a lot of pressure. So 1 atmosphere, 0 degrees, only for gases. This pertains. There's this relationship that under those conditions only, and I can't overemphasize that, because if I don't, it'll come back and say, well, you said, well, I said, no, only under these conditions, this is true. A gas, 1 mole of gas occupies a volume of 22.4 liters, okay? Remember when we were talking about the properties of solids, liquids, and gases. Solids have a known volume. Liquids have a known volume, okay? Gases did not. They occupy whatever volume, whatever container they were in, okay? So, but under these conditions, they all have a known volume. That is 22.4 liters per mole at 0 degrees Celsius and at 1 atmosphere, okay? And so here are all these gases. You got hydrogen, fluorine, ammonia, xenon, methane. They all have 1 mole, okay? And they all have the same number of molecules, good old Avogadro's number, but they all have different molar masses, and this stands to reason they're different atoms, right? Just like the small, medium, and large eggs. They have different weights, right? But they all share the same property of 22.4 liters per mole, okay? And guess what? That's another ratio. Liters per mole or moles per liter that you can utilize. All right, so this slide represents what I just stated. For 1 mole of gas, occupies a volume of 22.4 liters, only at 0 degrees Celsius and at 1 atmosphere. So we can utilize that to do some calculations. Question here says, what is the volume of 1.25 moles of argon gas? All right, well, analyze the question first. All right, you're given 1.25 moles of argon gas. So you got roughly 1.25 moles of argon gas. And you know, based on that relationship at STP, that 1 mole has a volume of 22.4 liters. You have about 1/4 mole more. What does that tell you? That your answer should be greater than 22.4 liters. It should, right? If you set that up properly. All right, so we can do that. And guess what? It's 28.0 liters. Now, 22.4 liters is a measurement. It's not an exact number. So therefore, 22.4 liters could be a factor with respect to sig figs, okay? Remember that exact numbers are not, and along with exact numbers, but atomic weights are not used. Molar mass is not used for sig figs. But in this case, we have 3 sig figs and 1.25 and 3 and 22.4. Our answer should have 3 sig figs. And that number is consistent with the fact that you got 1.25 moles of a gas. It is greater than 22.4 liters. If the number your answer was inverted, okay, meaning you got a number much less than 22, then you know that maybe you inverted your numbers, so go back and check. Okay. Second question here says, how many moles is 30.4 liters? So you're given the volume, you're still at STP, so you can use that relationship. And you can just plug it in there, and you can notice that my liters cancel, leaving me with moles of oxygen. Okay, moles of oxygen. So again, think about the numbers you're given. You're given 30.4 liters. Okay, now you know that 1 mole is 22.4 liters, but you're given 30.4. So I expect an answer that should be greater than 1. Sure enough, my answer is 1.36, which is consistent with what I was given number-wise. All right, now this one here, it says, what is the mass? So they're asking you for the mass. So that's an indication that should give you a flag to say, if I need the mass, guess what? I'm probably going to need the molar mass of chlorine gas. Again, chlorine gas. So do we use Cl or Cl2 for molar mass? Is chlorine diatomic? Have no fear of ice cold beverage? Yes, it is. Okay. And so the molar mass, no, chlorine is diatomic. Have no fear of ice cold beverage. All right. Yes, you got it. Cold for chlorine. All right. And so we set it up. We have the molar mass, excuse me, the 22.4 liters per mole, which gets us into moles of chlorine gas. And then we use the molar mass of chlorine because the diatomic is 70.94 grams per mole. Chlorine by itself is 35, I think, 35.45. So the chlorine gas being diatomic, make sure you use the right molar mass. All right, so that means that 4.5 liters of chlorine gas at STP weighs 14.2 grams. All right. This flow chart summarizes these calculations we just did, okay? And notice the intermediate. The intermediate is moles, okay? I cannot get from grams to volume without going through moles. I cannot get from grams to atoms or ions or whatever without going through moles. Now notice that it looks like it's one way, but you can go in multiple directions. If I go from grams to atoms, I can go from atoms back to grams, or I can go from atoms to volume, or grams to volume, or volume to grams, either direction. But to do all that, you need to go through moles. Now keep in mind, the yellow part, the volume, is only true when you're dealing with gas and you are at STP. Okay? At STP. So this moles is crucial. Now, we're showing you here simple calculations as far as volume and atoms, but the same is going to be true when we start calculating grams of A to grams of B. We can't go directly unit weight-wise, but we can if we know the molar mass and we know the moles. So molar mass, being able to figure out the molar mass is also important. So you got to know that scenario, the molar mass, to get to moles. And of course, Avogadro's number to get from moles to atoms or ions or whatever. And of course, this relationship, 22.4 liters mole to get to volume. Okay. All right. Here's a couple examples. How many grams is 17.35 liters of neon gas mass at STP? So they want to know how much does 17.35 liters of neon gas weigh at STP? So you're at STP. Now, sometimes they don't tell you STP, but they may say, it might be worded like at 0 degrees and 1 atmosphere. That should tell you I'm at STP. If they don't mention STP and if they don't mention 0 degrees and 1 atmosphere, then the only answer you have is not enough information. You can't do the calculation because that would not be a true statement unless you are at STP and unless you are working with a gas. Okay, so the first one is we write down what we're given, 17.35 liters. And we write down the units that we're wanting to obtain, grams per neon. Okay, the answer is there, but I just wanted to show you that's how I keep track of where I'm at and where I want to go to. Okay, because that aids me in setting up the next units, my next conversion factors to make sure I set it up properly. And so my first one I set up is because I am at STP, I can use that relationship of 1 mole is equal to 22.4 liters. And I set it up with liters in the numerator because I want liters to cancel, okay? Unit-wise. So I'm not even looking at the calculations. I'm just looking at the units right at this point. Okay, so at this point with the first conversion factor, I'm in moles, I'm in units of moles. And I'm not where I need to be because the question asked me how many grams. So I need the molar mass of neon gas, which I simply look it up on the periodic table. Neon gas is not one of the diatomics. It's simple 20.18 grams per mole. And so with that information, I insert my second conversion factor, keeping track of my units. You know, like I mentioned earlier, if you have moles and 1 grams, I multiply by the molar mass. And now I end up with 15.6 grams. Now you might ask, okay, I got 3 sig figs here, and I start off with 4 sig figs. You told me not to use the atomic weight or molar mass as sig fig determination, which is correct, okay? But I did mention that 22.4 liters is a measurement. It's not exact. So it could play a factor in your sig figs depending on the question. And in this scenario, it is a factor. I got 3 sig figs versus 4 for 17.35. So my answer would be in 3 sig fig format, okay? Remember, with respect to significant figures, it's simply not presenting more accurate data than the least accurate measurement that you have. That's all it's doing, okay? Yes, I know you can plug that in a calculator and you got 20,000 numbers. That doesn't improve your answer. That's inaccurate because you're being more accurate than the accuracy of your measurement. All right, so the second part was, all right, the next part is how many atoms does this 17.35 liters correspond to? So the first one, we figure out how much it weighed. Okay, now the next one is to actually calculate how many atoms of gas we have. So again, I write down what I'm given, 17.35. I write down the units that I'm looking for, okay? Your answer is given there, but the units. So that means that one, I'm still at STP, and I'm going to need the 22.4 liters per mole conversion factor, and then I'm going to need Avogadro's number. to get me into atoms. And so I set it up, again, keeping track of my units to make sure that units cancel out properly. My liters cancel. Okay, my moles cancel, leaving me with atoms. Okay, which is what the question asked for. And so I have 4.66 times 10 to the 23rd atoms. If I have 17.35 liters of neon gas and I am at STP, that gas would weigh 15.6 grams and it would have 4.66 times 10 to the 23rd atoms. All right, we're getting close to the end of this chapter here. All right, a while back we talked about density, okay? And density was nothing more than another ratio, which happened to be the mass over volume, okay? So all matter has density. And so if you know its mass, you know its volume, you can calculate its particular density. Well, we can calculate densities of gases at STP without even having to measure anything, because we know that at STP, there is a molar volume for every mole. There's 22.4 liters per mole. We also know the molar mass because we know the formula. And from the formula, we can easily calculate the molar mass by simply adding up all the atoms involved in the formula, okay? And it's given to you here as NH3. That is the formula for ammonia gas. It is possible that sometimes they don't give you that. They just say ammonia gas. So you might be familiar with the formula of ammonia gas. That being said, you can simply take the equation for density, which is the molar mass divided by the molar volume, molar mass of ammonia, 1 nitrogen, 3 hydrogens, has a total of 17.04 grams per mole. And the molar volume at STP is 22.4 liters per mole. Moles cancel, leaving us with units of grams per liter, which by definition is density. Okay? So we can calculate the density of gases at STP, which brings us to a final part here. It's called percent composition. This is pretty straightforward because you're already familiar with your percent composition per se, because you know that all your assignments are broken up depending on the percentage. The nomenclature exam is a certain percentage, the regular exam is a certain percentage, finals a certain percentage, labs a certain percentage, etc., etc. Okay, the way we calculate the percent composition is analogous to that. That first we have to write the formula, so we know what we need to know what the formula is of whatever compound we're given. Okay. From that, we then add up or calculate, determine the molar mass. Okay. And that we're halfway there, because now we simply, all we have to do now is multiply the contribution of every atom divided by the total molar mass. So in this case, water has a molar mass of 18.02 grams per mole, okay? And the water, the hydrogen brings in 2.02 grams per mole. So those units are incorrect. The units should be grams per mole, grams per mole. They're gonna cancel out anyway, okay? So make a note of that. It should be grams per mole. All right. And so 2.02 divided by 18.01 times 100 gives us 11.2% hydrogen. The oxygen gives us 8. Hold on. The oxygen gives us 88.8% oxygen. Okay. So what that means that every water molecule out there in the world, and as far as I know, the universe, if we analyze it, it has a composition of 11.2% hydrogen and 88.8% oxygen. Okay, that is the percent composition. So we can take any compound. Okay, let's take this one, TNT. Does anybody by chance know what TNT is?
Do you mean like the explosive?
Certainly is. It's dynamite. Dynamite is also, it comes from, its chemical name is trinitrotoluene. Hence, it take the T from tri, the N from nitro, and the T from toluene, and you get TNT, otherwise known as dynamite. Its formula is given there. It's 7 carbons, 5 hydrogens. We have a total of 6 nitrogens and 6 oxygens. Okay. Now, does anybody by chance know who invented this? Trivia question, kind of side note. Let me give you a hint. There's prizes awarded every year for different disciplines. Very impressive award. They give it out for peace. They give it out for medicine. They give it out for chemistry. They give it out for physics. Anybody know what that prize is called? That's correct. There you got it. Nobel. Nobel was a chemist, scientist, and he's the one that developed TNT, which is amazing because this is a very touchy chemical. Very touchy. Anyway, the question here says, find the percent composition for TNT. Well, obviously, if it's something like this, you'll be given the formula, but it could be the percent composition for, who knows, ammonium nitrate, something like that. Any of the ions we talked about. But anyway, you're given the formula. And so we got to calculate the molar mass. Okay, so always use the atomic weights from the periodic table. And so from the periodic table, the atomic weight for carbon is 12.01. There are 7 of them, so that gives us a total of 84.07 grams per mole. 5 hydrogens at 1.01, total 5.05 grams per mole. 3 nitrogens at 14.01, total 42.03. Oxygen, 6 of them at 16 apiece, gives a total of 96.00. So we have a grand total molar mass of 227.15 grams per mole. Okay, that is the molar mass for TNT, otherwise known as trinitrotoluene. Okay, so here, if I weigh out 227.15 grams of TNT and weigh out very carefully, because it's very shock sensitive and heat sensitive, I have 1 mole, or 6.02 times 10 to the 23rd atoms of trinitrotoluene. Okay, once we got the molar mass, we got the individual contribution for carbon, hydrogen, nitrogen, and oxygen. We can go through the math for each one. We come up with 37.01% for carbon, 2.22% hydrogen, 18.5% nitrogen, and finally 42.26% oxygen. Now, this is something we do in the, quote, real world of science and chemistry. Every time I made a new compound, after we go through a process of purifying it, we would send a sample out. Now, we knew what we put into the system. We knew what we were striving to obtain, so we can back calculate the percent composition. Then we send a sample out to the labs, they do analysis. We tell them, give us the percent composition of carbon, hydrogen, sulfur, or any element that you're looking for. And then you compare it with the theoretical amount, numbers that you have, and that adds to the fact that you made whatever compound you made, along with the other instrumentation that you do and you run that sample. But yes, this percent composition is something that is utilized quite a bit in the world. And the unique thing about this is unique for trinitrotoluene. And this is unique for any compound. They have their own percent composition. All right. All right. So try this at home. The question is, how many liters will 3.425 grams of carbon dioxide occupy at STP? You should come up with an answer of 1.74 liters. Okay, then the question is, how many molecules is 3.425 grams of carbon dioxide? You should come up with 4.68 times 10 to the 22 molecules. And then they ask you, how many grams will 3.0 times 10 to the 15 molecules of carbon dioxide mass? And your answer should be 2.2 times 10 to the negative 7 grams. So try those at home. If there is a problem with it, let me know, and you can email me, or we can talk about it next Friday, and we can go over it. So make sure you calculate. But with that being said, that, ladies and gentlemen, is the end of chapter 12. And that's what next week's exam's about, 10, 11, and 12. Okay? So other than that, is there any other questions or comments? I'm going to stop it there, obviously, given the time that we have. I still, if you're more than welcome, because I do have classwork on Tuesdays and Thursdays. I got a 2:15 class and a 4:15 to, what was it, 5:30 class, Tuesdays and Thursdays. You're more than welcome to hop in those classes, to use the same link that you have and jump in there. We're approximately the same spot. In fact, they're only like 2 slides ahead of you with respect to chapter 13. And what I'm doing with them, because we meet twice a week, that every Thursday is basically a study day from this point forward, because the semester is pretty much ended. Really, we don't have too many weeks left. We only got 3 chapters left to do. And so every Thursday in those days, students come in with questions. We basically have an office hour time to bring in any questions that you want. So feel free to jump in, on those days. All right. Any comments or questions?
I had a question on the